Well, it's a pleasure to have L Wen from Perth, the beautiful town of Western Australia, and participating in David Blair activities also, no?
David is my colleague.
Yes. And okay, welcome.
Thank you. And good morning. I really thank the conference organizer for having me here for a second time. I noticed the audience is a little bit different. I'm more an astrophysicist. This work, I'm going to talk about the source localization of the third generation gravitational wave detectors and the implication to cosmology. And my collaborator is Professor Wen from the USTC. Before I start, I shall mention I'm a member of the LIGO Scientific Collaboration, one of those 1,000 authors for LIGO papers. Here's the outline of my talk. First, as usual, give an introduction. Then I'll talk about the localization capacity for gravitational wave detectors, specifically for binary neutron star or neutron star black hole systems with a good reason. And then I talk about the implication. At the end, I will give a summary. So the work I present here is already actually under revision. That means it should be published soon. It's also available on arXiv. Just a low-level introduction. So as Hubble told us, our universe is expanding. So at the local universe, the expansion follows the so-called Hubble law. That means the receding velocity is proportional to the distance, the luminosity distance, by a constant called Hubble's constant. So therefore, Hubble's constant, that's the expansion rate of the universe, can be measured by measuring the redshift, say, of the galaxy, and the distance, right? That's for local universe. Of course, the measurement of the redshift will be affected by local velocity field. For instance, in this figure, you see that here is the redshift. Here's the distance. It's more or less a constant slope, but you see this drop here. That's an effect from the Virgo cluster, the local field. So I'm an observer, so all I'm talking about is about observations and related to the theory. So our universe is not just expanding, the expansion is accelerating, and that has been sort of confirmed or indicated by the measurement at high redshift. Actually, still the redshift and distance relation. So here you can see at low redshift, these are the data points. It's still a constant slope here, but then you can see at high redshift about up to 0.8-ish here. You can see tilt up. That indicate the expansion is accelerating, and 3 Nobel Prize have been given to 3 scientists, leading to this results. One is from Australia. Yeah. And the measurement method is used supernova type 1a. So what's supernova type 1a? Why is it so special? Supernova type 1a is basically it's a binary. You have a white dwarf here, and you have a companion star accreting onto the white dwarf. When the matter accreted onto the white dwarf is so much that the mass of the white dwarf exceeds the so-called Chandrasekhar limit, about 1.4 solar mass, that means the white dwarf will collapse, and it will have supernova, and that's so-called type 1a supernova. And this kind of supernova is very special in the sense it has a very unique light curve, in the sense that, say, it actually powered by the radioactive decay of nickel and cobalt isotopes. And what they found is that so-called Phillips relation, the absolute magnitude, which basically can be translated into luminosity. So luminosity of this supernova type 1a is actually directly related to the decay of the apparent magnitude, that's like flux, right? From the peak to about 15 days after. So this slope, this is delta M15 here, can tell you the luminosity of the supernova type 1a. That's so-called Phillips relation by staring at about 100 samples in the beginning to start with. And what we are doing, once you know the luminosity, you know the flux, you get distance. See, all we want is distance. Redshift is relatively easier in a way. So what we really need is to calibrate Phillips relation and assume all the supernova type 1a follow similar characteristic of this. That's a big assumption. And therefore, you need multiple calibrations for that. So that's so-called distance ladder. So what do you do? Because first of all, we can get the distance of nearby stars by so-called parallax. Because the Earth is going around the sun, therefore, the nearby stars have their apparent sky direction will change as the Earth goes around the sun. And by measuring this distance, you get the distance to these stars. So, but this doesn't reach far. However, there's something else. It's called surface variable. These are pulsating stars. So that means their light curve pulsate at a fixed period. So what has been found is that the period of this pulsation is proportional actually, related to the luminosity of it. And this is actually one of the reasons, that's how Hubble discovered our galaxy is not alone, because he actually found a surface in the Andromeda galaxy, and he knows its relation, and he calculated the distance and found that Andromeda is way far away from our size of the galaxy. And that's how surface variable, because surface variable is bright, so therefore you can see further away. So therefore, first step, you do parallax of the surface, get their distance, right? And then you observe, you basically have to calibrate the relation of the luminosity and period. And then you observe type 1a supernova at nearby universe where they are also surface variable. So you use that distance to calibrate the Phillips relation of type 1a supernova at a bit further away distance. And then you assume further down the road, this relation holds. That's a big if, because that's high redshift events. So, but that's how measurement is done. Yep. So let's see. Now, so the last one relies on measurement of the distance. The second different method is basically to measure the temperature anisotropy of the cosmic microwave background. And actually, this is the Planck's all-sky temperature map from the cosmic microwave background. These are the relic radiations from the beginning of the universe, and we basically capture the moment when the photons at the last scattering surface, when the photons go free. But it's supposed to be isotropic, but it is. But when you look at a smaller scale, you find the anisotropy, small differences. And these are the imprints of the density fluctuation, which are the seeds for the large-scale structures we observe today. Therefore, measuring the temperature anisotropy at different angular scale will tell you how the universe evolves. And this is the probably famous figure. Its resolution is not very good. X-axis, basically angular size. The angular size going this way is smaller. And the y-axis, you basically do multiple expansion, it's the power. And the feature of this peak are basically the feature of the model of the universe. It's a balance between the radiation. Radiation tries to smooth out all the irregularities, right, in the density profile, but the gravity tries to bring it in, try to intensify. Therefore, the balance of the radiation and gravity basically cause certain oscillation, and these peaks reflect the resonance of one of those modes when the photon decouple from it. So therefore, what we do is you take the measurement of the temperature and anisotropy, you do this transformation at different angular scale, and then you fit with your, that's really not readable, sorry about that. You fit with different kind of models and find the best fit model. And then the Hubble's constant is inferred from these models. Yep. And of course, the measurement is generated with many parameters. That's the limitation of the measurement. Currently, there's a tension in the measurement at Hubble's constant. There are many different measurements, but so x-axis is Hubble's constant. The central value is somewhere here. And that's the CMB measurement. Assuming the Lambda CDM model universe, you get about very small error bars right here with small. And supernova type 1A, that's the second best one. Basically, it's here, and see the error bar here. And they are 3 sigmas away. For an observer, 3 sigma means significant. Therefore, the 2 different measurements have different measurement of the Hubble's expansion rate. So that's one of the reasons. And now, what the topic of? Sorry?
How to choose, right?
Yeah, so that's why we need independent measurement. That's where gravitational wave is coming in. Or it's about introduction. See, remember last year we have the measurement of the gravitational wave and light together from the merger of binary neutron stars. Therefore, once you have optical counterpart, you get redshift because you get the association of the galaxy. And gravitational wave actually give you independent measurement of the distance. We don't need distance ladder. With 1 data point from last year, that's our result. The big one was just 1 data point. It will be refined when we have more measurement. And you can see sort of agree with all the measurements. But, right? So that's the topic of this talk. So the other thing is, can we measure the acceleration of the universe? As we know, the dark energy is driven. The acceleration is driven by this so-called dark energy. When you said dark energy, that just means we don't know where it is, right? So another topic is, can we try to figure out what dark energy is? This is like 70% of the total density. And what we characterize this is because the dark energy we characterize by so-called equation of state, defined as the ratio of the pressure and the density. Because from this, you sort of can tell, for instance, we could decompose it into 2 components. One is a constant, that means it doesn't evolve with redshift. The other component is evolved with redshift. We want to measure this omega 0 and omega A. If this dark energy is completely driven by cosmological constant, it should be, the evolving part, should be 0, right? And here with normalization, -1. And here are the measurements. So current measurement, they do not, it's still quite uncertain. So there, gravitational wave, again, can come in to help. So now I really go into the topic. Those are just introduction. So therefore, the topic is gravitational wave as an independent probe to the expansion of our universe. Although I'm sure everyone heard about it, but here I put a video on. See, I'm an astrophysicist, so we make videos to make you believe what we have seen. So here is a summary from LIGO.
On August 17, 2017, a gravitational wave, CHIRP, was recorded by the National Science Foundation-funded LIGO observatories, and less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. Researchers quickly realized these 2 fundamentally different types of waves could have come from a single neutron-star merger. If so, it was critical to identify exactly where this had taken place in the sky, and if the explosion could be seen by other telescopes. The Fermi data indicated the burst came somewhere from a patch of sky covering about 1,200 square degrees, an area equivalent to 6,000 full moons. Adding information from an independent gamma ray detection from the integral satellite, the search area was further reduced. The LIGO observatories placed the source somewhere in long, narrow strips of the sky, one of which overlapped with a target patch. The Virgo Gravitational Wave Observatory in Italy, working in conjunction with LIGO, should easily have been able to detect a signal of this strength, but saw almost nothing. This was an important piece of the puzzle, since any gravitational wave observatory has a small number of blind spots where it cannot detect an incoming signal. Restricting the source location to Virgo's blind spots further narrowed the search area down to approximately 28 square degrees, or 140 full moons. Around 50 candidate galaxies were identified in this area for follow-up observations using optical telescopes. Less than 11 hours after the first detections, astronomers using the Carnegie Swope telescope identified a previously unseen blip of light in the outer reaches of the galaxy named NGC 4993. Several independent confirmations were reported from other telescopes over the next hour. The first ever optical counterpart to a gravitational wave event had been found. Knowing exactly where to look, astronomers began an unprecedented campaign of follow-up observations using more than 70 telescopes around the world and in space. During the course of the next 2 weeks, the neutron-star merger was detected across the entire electromagnetic spectrum. The gravitational wave data have, for the first time, provided a direct measurement of the masses and orbits of a neutron-star pair before their collision and merger. The data also enabled ongoing follow-up observations across the electromagnetic spectrum, characterizing the explosion and revealing how such unimaginable events have played a formative role in shaping the world around us.
So one thing we should take from this video, and besides the story, is that the breakthrough in the localization of the gravitational wave event is decisive for the optical follow-up observations, because optical tests cannot see, they don't have wide field of view. They need to know where to look. Thanks to Virgo, in a way, even though they did not see anything, it helped because it's operational. As long as it's operational, it would provide information to limit the sky directions of the source. So that's how it limited itself to 28 square degrees. Even within 28 square degrees, you have 50 galaxies, you check one by one. I believe the optical counterpart was found on the fifth one or something. So that's why localization is very important here. And the second thing is that we know that from gamma ray burst, right, that we can see far into the universe, and there is a way to get redshift out of it. Now, for those who want to sort of know a bit more, how exactly do you measure the luminosity distance from the gravitational wave, is that first, each detector, gravitational wave detector, this L-shaped microsync interferometer, they give you one data stream, which is a linear combination of the two wave polarizations of gravitational wave, if Einstein is right. Einstein thinks there are two polarizations, that's what we think, right? So therefore, however, gravitational waves, these two polarizations, that's from binary coalescence, say binary neutron star or neutron star black hole, it's the same. It's a relation, it depends on this so-called chip mass. So it's a mass, and it depends on frequency evolution and the distance, and this is the inclination, the viewing angle relative to the binary. So what you can see is when we do the detection, because fortunately we can do theoretical calculations about the waveform. So what detection did is that we do the so-called matched filtering. That's actually doing correlation of the expected waveform with the data. So this way, we actually can match the phase very well and get the mass out. The so-called chip mass can be well determined. So now we need at least two detectors, right? Because you have two polarizations. Therefore, you have two detectors to separate these two to measure individual polarization. But then your luminosity distance is actually degenerate with the inclination angle of the binary. So that's basically how our measurement is done. We actually have it depends on the accuracy of the inclination, and you need at least two detectors to separate two polarizations. That's one of the key I need to.
Say no distance lines needed. Everything is needed. You thought about localization. We have at least three dimensions. There's no
Right. So this one, we don't need things like parallax and surface, and you have to assume certain things. But at least, what did I do? All right. So that's basically what we have done. Then, and that's probably all know, of course, the distance measurement can have the imprints of all these parameters from cosmology, the expansion rate, the Hubble's constant, the mass density, the curvature density, and the equation of state of that two components. And we can use the low redshift measurement directly get Hubble's constant, and we need high redshift distance measurement to get the acceleration or the equation of state of dark energy. However, for LIGO's horizon, it's only like a few hundred megaparsec. So LIGO alone, it can see nearby events, but not further down. So that's why we are talking about third generation detectors. We assume a big fraction of the gravitational wave events will give us electromagnetic counterpart, therefore provide the redshift information. That's the assumption. Also, we only consider systems with neutron stars because we need matter to generate electromagnetic radiation. And unless, like us, binary black hole for some reason get some matter, then you can also have electromagnetic counterpart from binary black holes. That's actually I gave the talk last time on that one. So here's the result from this one single point of binary neutron star. Here's I apologize for the resolution of the image. So x-axis is the Hubble's constant, and you can see, and y-axis here is the inclination angle, the cosine I. You can see it really depends on how well you can measure the inclination angle. But our result is consistent because we have such a large error bar with all measurements. Now we're talking about third generation detectors. So there are two leading designs. One is basically European design. It's underground, triangular shape interferometers like this. You know, there are three V-shaped laser interferometer, 10 kilometers apart. This mathematically is equivalent to two L-shaped laser interferometer, just like LIGO, with 7.5 kilometer arm length. And because it's underground, it reduces the low frequency noise. And therefore, ETD, this European design, not only it has like effectively two detectors at the same site, which help resolve the polarization, and it has low frequency sensitivity. These are the two features of the ETD design. And we also have Cosmic Explorer, the CE design. That's American design, more or less. They said, okay, since what we are measuring is the fractional change of the length, therefore, how about I just increase the arm length of detector by a factor of 10? Well, of course, it's not that simple, but that's basically the principle. So their design is basically just extended the LIGO to arm length of 40 kilometers. But remember, it's still one L-shaped one. It cannot, just one detector cannot resolve two polarizations, which is very important for directional, for the measurement of the distance. Now, I want to talk a little bit about a low frequency sensitivity, the importance of it in terms of measurement for sky direction, and therefore affect the distance measurement. That's one, because we were trying to feed some information for those design team, you know, how important the low frequency sensitivity is. So as I just mentioned, so if you look at the blue line, that's the ETD design. It has y-axis is the noise spectral density, x-axis is frequency, and green line is the CE design, the American design. You can see the CE design around a few hertz, around 10 hertz, it has basically no sensitivity. However, for ETD, even though it's a bit shaped, but it has some sensitivity down to a few hertz, and that we found actually make a huge difference. You was like, oh, it's not that great either, but actually it's very important. And another thing about the third generation detectors is that it's going to be 10 times more sensitive than advanced LIGO. That means the volume is 10 to the cube, 1,000 times bigger. So we therefore expect possibly a few times 100,000 binary neutron star events, neutron star black hole event, it's really depends, up to redshift of 2. So we can have lots of events and to high redshift. That's really good for cosmology. So in our calculation, we actually assume the detectors, we do one detector because else the one detector is useful for ETD. We assume the detector either in the US, Europe, in China, Australia, the nominal place. Africa, that doesn't make a huge difference. The only thing matters is the baseline. So actually only the baseline matters, the location doesn't. And we actually compare the design of two detectors. But one thing I want to focus on is the angular resolution, how well you can measure the sky directions and the distance, if they are related. Now, if the signal is short, like now LIGO, you consider the detector doesn't move, right? And basically, the angular resolution is basically just a diffraction limit. It's basically, that's what we have on 2010 paper. It's basically, this is error area. So therefore, it's inverse proportional to signal to noise ratio square and frequency square, and the area formed by detectors, the projected in the direction normal to the gravitational wave direction. And of course, it's weighted by signal to noise ratio. So that's just diffraction limit, basically, in the context of gravitational wave. However, when you have better low frequency sensitivity, your signal is much longer. And if you look at the BNF, it could be 1 day. That means the detector is actually going around the Earth. Therefore, even if you just have one detector, it's equivalent for this one detector. It's equivalent to putting several detectors along the trajectory of this one detector. Therefore, it has a baseline. So what we found already in 2010 paper is that for actually at that time, we consider LISA, because LISA is going around the sun. And what's going to happen is that in the beginning, the longer the observation time, the better, because you are forming bigger baseline, right? But once you finish one circle, your baseline no longer increase much because it's basically just this. Okay, so I hope it's still working. Therefore, if this third generation detector is on Earth, if the signal duration before it's like about 1 day long, the longer the signal, the lower the low frequency cutoff, the longer the signal, the better the localization and increase really fast. So one thing is we propose for detectors, you try to lower the low frequency sensitivity as much as possible because you gain a lot, not just from signal to noise ratio, but also, I got the time, but also from the area, from the baseline. But once you pass 1 day anyway, you are sort of, you rely on the increase on signal to noise ratio. And that's one point I really want to make. And next slide is sort of just to substantiate what my claim is that we can actually calculate the duration of the signal and as a function of the low frequency cutoff. And you can see it's nearly a third power, a third. So you can see for BNS system, it's nearly 1 day. And we can actually do, we assume the noise spectrum is flat. You can actually see this turnaround time for BNS is about 1 day, just as expected. Yeah. But of course, our noise curve is slightly different, so therefore we put it on ETD, because remember it's not flat. The last one is flat, we just want to, for a sanity check, this one we just put in a real one, and you can still sort of see the turnaround. And you can see the angular resolution, you increase the low frequency sensitivity, this is a low frequency cutoff, it's a steep improvement on angular resolution, and then after 1 day you don't. So this is a very important part, and that's the main point, one of the main points we made. And now talking about cosmology, what can we do? We do simulations, right? So we do this so-called violin plots at different redshift and do lots of ensemble, and then these are the average, the median of angular resolution in logarithmic scale. And that's for one ETD detector. Remember for CE, because it's one L-shaped detector, you cannot localize. So for one CE detector, you cannot localize, but for one ETD detector, because of the low frequency sensitivity, and also because it can actually resolve two polarizations, because it's equivalent to two detectors at the same site. It actually you can already do cosmology using one ETD detector. And what we have found is that the angular resolution and the distance determination is, for one ETD, is already as good as LIGO Virgo 3 detector at advanced sensitivity. So therefore, if you build one ETD, you already get an advanced LIGO network. So that's another solution, another conclusion we have, and we can already, one ETD already can test Hubble's constant using redshift at 0.1 data. Ooh, I'm basically done. So for equation of state, we do the same simulation, and we compare with the future missions, right? Because now we have high redshift data. And we found with the canonical number, basically gravitational wave detector can do as good, can measure the equation of state of dark matter as good as Planck, future Planck, and the future supernova type 1a. As a summary, gravitational wave detection is really can provide independent measurement of the expansion rate of the universe. And if you only build one detector for third generation, the design that can separate polarizations and can have good low frequency sensitivity is a plus. It's a good thing to have for cosmology. And it's also possible in the future, gravitational wave detectors measurement is going to be the best. Thank you.
Thank you very much. Questions?
I'd like to ask a timing question. I see some of your proposal and discussion of detectors was from 2010. Why are there no such detectors? It takes so long.
2010? Oh, no, that's my paper. It's a theoretical paper. It's just
It
a
seems to be too long. These things are not so impossible to construct. So why don't you construct?
the detector.
Yeah.
Well, if you give me the money, at the end of the day, it's money, right? And politics.
Luca?
Just have a short comment. I wanted to point it out that the luminosity distance that you get from gravitational waves depends on the assumption of Einstein's gravity. If the propagation equation is different, like in any model, then you get a different distance, which we can call gravitational wave distance. So that depends on the Planck mass at emission and that observation.
Indeed, because when we calculate waveform, we do assume Einstein's general relativity, and we do assume the two polarization, which again is Einstein's theory. Yes, I agree with you.
More than the two polarization is the fact that the propagation equation depends on that.
Indeed.
So it's not completely model independent.
Indeed, we assume, for that to work, we assume Einstein's general relativity, yes?
How your results are sensitive to the population of binaries that you are assuming, because we know what we have up to 4 orders of magnitude in the estimates of the binary Newton-star population of the Newton-star merger. I think you code there the most optimistic value possible.
Yeah, for that, I agree with you. So the question is how about the event rate, right? Which is a several order magnitude, uncertain. So are you going to get so many events? But from what we have seen, we're actually quite, it looked like it's fine so far, but I agree with you. It can be uncertain by orders of magnitude.
Yeah. Can pulsar timing arrays make a contribution for this equation of state, or is it pulsar timing arrays? Can they make a useful contribution here, or is they not competitive?
Indeed, pulsar timing array is also measuring gravitational waves, right? But for binary supermassive black holes, I guess the question is, where are they going to get redshift? Yeah, that's if you get redshift and distance, and that's far away, right? Yeah, fine. But redshift is a little bit issue for pulsar timing.
Well, if there is no more urgency, well, it's very interesting, and I think it will be very interesting to find the localization both solely by electromagnetic signal and solely by gravitational wave, and see if they agree or do not agree.
Yeah, so for the first binary neutron star, indeed, we have both localization agree with each other. That's how we have confidence, right? So because for the first one, we have Fermi's localization, and we have the 3 gravitational wave detectors. They are all independent, actually.
Yes, to check the independence. Okay, thank you very much.
Thank you.